Year 12s, hello and welcome to the first of 3 videos on wave-particle duality. Now, if you recall, the idea of this is we are rapidly running out of time this term, and your job this weekend is to watch all 3 videos, possibly take some notes as well, because you won't be being taught this in class. When we come back next week, I will have assumed you'd watched all of this. I may give you the opportunity to ask any clarifying questions, but I intend from there to move on to the next topic so we don't run out of time. Okay, so this first video will deal with X-rays, how they are produced, and the characteristic X-ray spectrum that we see when we look at the graph of frequency against intensity. Okay, so X-rays. X-rays are very high energy electromagnetic radiation. They have wavelengths that are significantly shorter and frequencies that are significantly higher than visible light. So we are talking a factor of 1,000 to 10,000 times. Now, the production of X-rays is another example of a phenomenon that can only be explained if we use the photon model of light rather than the wave model of light. So they're further evidence for the existence of photons. So what we have here is a very simplified diagram of a typical X-ray tube. And we'll go through the parts of that X-ray tube and what they do. So the first thing we need to know is that the guts of the X-ray tube are contained within an evacuated glass tube. So all the air is being sucked out of it, and that's to avoid energy loss when electrons collide with gas molecules inside the tube. So on the left-hand side here, we have a metal filament through which a current is run at low voltage, and the purpose of this is to bring those electrons to the surface of the filament. Now, in this way, it's very similar to the Teltron tube you've been using in class. Once the electrons come to the surface, a large potential difference is placed across the 2 ends of the tube. The filament is held at a negative potential, and the target, where these electrons are going to collide and produce X-rays, is held at a positive potential. The size of the potential difference between these 2 ends is typically in the range of tens of thousands to hundreds of thousands of kilovolts, so quite a big potential difference. This potential difference tears the electrons out of the filament and accelerates them towards a metal target. Now, the metal target is typically made out of a small piece of tungsten metal. And the reason we use tungsten metal is it's a tough metal that can withstand continuous electron bombardment and the associated high temperatures that comes along with that electron bombardment. Now, the tungsten target is set within a larger piece of copper. And the idea here is that the vast majority of energy that's released in an X-ray tube is actually in the form of waste heat. And if that waste heat wasn't removed, it would lead to the X-ray tube melting or burning out. So copper is used because copper is a very good conductor of heat. The copper conducts away this waste heat out of the tube and into cooling fins that are mounted on the outside where it's radiated off into the air. And you can see lastly, by looking at that target, that usually it's slanted at an angle. So the idea there is when the electrons collide with the metal target and produce X-rays, those X-rays will go off out of the tube at 90 degrees to the direction of the electron beam. So in this diagram here, I have indicated the direction in which X-rays are emitted by those green arrows. Okay, now before we get to the actual process by which the electrons are produced, we should probably first have a look at a typical X-ray spectrum. So when I say X-ray spectrum, I mean a graph showing the different frequencies of X-ray radiation that are found in a beam of X-ray light and the intensity of each frequency, in other words, how strong that particular frequency is. Now, if you look at the top diagram on the right here, you will see the shape of a typical X-ray spectrum. It consists of a smooth part with a peak, and over the top of that we have a number of short spikes as well. Now we'll deal with the smooth part first, which we refer to as the continuous spectrum. And if you look at that, you can see that the continuous spectrum extends up to a certain maximum frequency, Fmax. And then beyond that, there are no more X-ray frequencies present in the spectrum. So we'll have to explain that a bit later on. Now the second thing to note is that these little spikes you can see in the spectrum, they are sometimes referred to as characteristic peaks. And the X-ray frequencies that are associated with those characteristic peaks are referred to as the characteristic X-rays for that particular metal target. Okay. Now, in the lower diagram on the right there, you will see a number of different spectra have been drawn in there. There's a number of different lines. Each of those corresponds to a different voltage that's used in that tube. So the innermost one, the one that ends at the smallest F value, in the bottom left-hand corner of the spectrum, that would be the lowest voltage. And then as the voltage is increased, you can see that the spectrum extends further to the right. So what that's telling us is that the maximum possible frequency in an X-ray spectrum is dependent on the voltage. As you increase the voltage that's used in the X-ray tube, you also increase the maximum frequency. Now, the other thing to note here, it's not very well shown in this diagram, but these little characteristic peaks do not appear in the X-ray spectrum until you get to a certain tube voltage. Once you've reached that tube voltage, any voltages beyond that will always contain those characteristic peaks at the same frequency values. So that tells us that the production of these characteristic peaks has got something to do with the voltage used in the X-ray tube, which of course determines how much energy the electrons carry when they bombard the target. Now, in addition to this, one last thing to note about these spectra. We're talking here about a tungsten target. However, it is possible to use different metal targets in an X-ray tube, and when that is done, you will always see characteristic peaks, but those characteristic peaks will occur at different frequencies for different metal targets. So that also tells us that not only do the characteristic peaks have something to do with the incoming electron energies, they also have something to do with the structure of the metals themselves. But anyway, we'll come back to that a bit later on. We'll start by explaining how the continuous part of the spectrum is created. Now, to understand that, we need to understand what happens when electrons pass close to an atom within the metal target. Now, the electrons are negatively charged, and the nucleus of one of those metal atoms is positively charged. So if the electrons happen to pass close to that nucleus, they'll be attracted towards it, and they'll be deflected out of their original path. You can see that they're on the diagram to the right. Now, as they get attracted towards the positive nucleus, they'll slow down, as well as change direction, and this will cause them to lose some of their kinetic energy. Now, from the work of James Clerk Maxwell, which we looked at earlier, we know that when a charged particle experiences acceleration, it will lose energy in the form of electromagnetic radiation, or in this case, a photon. So what's happening here is the missing kinetic energy for these electrons that slow down and change direction is carried off in the form of an X-ray photon. Now, this process is referred to by the German name for it, which is called BREMSSTRAHLUNG, which is German for breaking radiation. It's the radiation produced when an electron is braked or slowed down. Now, the amount of energy that's released depends on how much the electron is deflected. If the electron is deflected through a larger angle and slows down more, then it has experienced a greater acceleration, and therefore it will lose more of its kinetic energy in the form of a higher energy X-ray photon. Now, we've illustrated that in the diagram to the right. There are two electron paths drawn there, a red electron and a blue electron. You can see that the blue electron is deflected through a greater angle and therefore experiences more acceleration. And we've represented that there by having that blue electron release a higher energy X-ray photon. You can see if you look at it that the way we've drawn that X-ray photon, we've drawn it with a shorter wavelength. And we know that as you reduce the wavelength of a photon, you increase its energy. Now, there are a number of different ways in which electrons can be deflected by a positive nucleus. So therefore, there will be a range of different X-ray photon energies when that occurs. And that explains where that continuous spectrum comes from. The range of that continuous spectrum represents all of the different possible frequencies caused by all of the different possible ways in which electrons can experience Bremsstrahlung and be deflected when they pass near a nucleus. The peak on the continuous spectrum just represents the most statistically likely way for an electron to be deflected. That's the most common one. Now, this is a little bit of a hard one to wrap your head around just by looking at static pictures. So in the description for this video, I will put a link to a short little YouTube video, not my own creation, that has an animation of Bremsstrahlung. It'll give you a bit of an idea of exactly what's going on. Now, we know there's a maximum frequency present in the X-ray spectrum, and that no further X-ray photons are seen beyond that frequency. So how does that occur? Well, the incoming electrons carry a certain amount of energy, and they lose that energy during this process. Now, the most these electrons can lose is all of their energy. And the frequency that corresponds to losing all of their energy as an X-ray photon, that's the maximum frequency. So, for example, if the electrons incoming carry 100 kilo electron volts of energy, then that's the most they can lose. They lose all of that 100 keV of energy in the form of a 100 keV X-ray photon. It's not possible to lose anything beyond that, so you can't have a 150 keV X-ray photon if the electrons themselves only carry 100 keV on the way in. So that's why you have a maximum frequency in your continuous spectrum. And that maximum frequency is produced when an electron just basically collides head-on with the nucleus. If they collide head-on with the nucleus, they will lose all of their kinetic energy in that process, producing the X-ray photon with the maximum energy and the highest frequency. Okay, so that's the continuous spectrum explained through this process of Bremsstrahlung. Now, we'll just have a look at a quick derivation of a formula which will allow us to calculate the maximum frequency, and then after that we'll go on to consider the characteristic peaks. But firstly, to derive an expression for the maximum frequency in an X-ray spectrum, we have to first understand that as these electrons move between the two ends of the X-ray tube, work is done on them by the large potential difference. And the work done on them by the large potential difference will be given by E delta V, where E is the charge on the electron, and delta V is the potential difference across the tube. Now, the work done on the electrons will be gained by them in the form of kinetic energy. So therefore, the work done will be equal to the kinetic energy of the electrons as they strike the target metal. Now, in the case of an electron losing all of its energy, that kinetic energy will be turned into a photon. And we know from Planck's law that the energy of a photon is given by hf, where h is Planck's constant and f is the frequency of the photon. So therefore, the maximum energy photon, hf max, will have an energy equal to the work done, E delta V. So you can see on the second line there, we've equated those two quantities, and then the last thing we do is rearrange that equation to make the maximum frequency the subject of the equation. So we've got maximum frequency, which sometimes also referred as the cutoff frequency, is equal to E delta V over H. Pretty simple. Now let's have a look at a quick example of how this formula can be used. There are two examples in my notes. I've chosen to go through one of those only. It will be worth going over my notes to have a look at this in a little bit more detail. Okay, so example one. Suppose we have an X-ray tube which has an operating voltage of 62 kV, in other words 62,000 volts. So we want to determine three things. Firstly, part A, the kinetic energy of the incident electrons upon striking the target. B, the maximum frequency present in the X-ray spectrum. And C, the minimum wavelength present in that spectrum. Okay, so let's start with A. We know that the kinetic energy these electrons carry when they strike the metal target will be equal to the work done, which is E delta V. So it's pretty simple. We just put in the charge on the electron, multiply that by the tube voltage, which is 62,000 volts, or 6.2 times 10 to the power of 4. And when we do that, we get a kinetic energy of 9.9 times 10 to the negative 15 joules. So that's one way of solving it. A second way of solving it would have been to realize that the incoming electrons have work done on them in electron volts of 62 keV, or 62,000 electron volts, and then convert that quantity into joules. We've given you exactly the same answer. So two different ways of thinking about the same result. Okay, so part B, what's the maximum frequency present in the spectrum of emitted X-rays? Well, we can just use that formula we had before. I've written it slightly differently down here. I've used Planck's law instead. F max equals the maximum energy divided by H. Now we just found the maximum energy in the previous part. Maximum energy is equal to the kinetic energy carried by the incoming electrons. We worked out that was 9.9 times 10 to the negative 15. So now it's just a matter of dividing that maximum energy by Planck's constant and that gives us a maximum frequency of 1.5 times 10 to the 19 Hertz. So in the X-ray spectrum for this particular example, no frequencies would be seen beyond 1.5 times 10 to the negative 19 Hertz. That's our maximum frequency, or our cutoff. Okay, so now we know that. Last step, what's the minimum wavelength? Now we know from the wave equation that the wavelength and the frequency, when multiplied together, always equal the speed of light, c. So when you have the maximum frequency, you will also have the minimum wavelength. As one gets bigger, the other one gets smaller. So we can see here we've taken that wave equation, we've rearranged it to make the minimum wavelength, lambda, the subject, and then we've put in the values from the previous steps. And when we do that, we get a wavelength of 2 times 10 to the negative 11 meters. Okay, so pretty straightforward stuff. And as I said, there's a second example in the notes. You may want to refer to that for a little bit more practice. Okay, so having been through the continuous part of the spectrum and how that works, let's talk about these characteristic peaks, because these are a completely different process to the BREMSSTRAHLUNG process that produces the characteristic spectrum. Okay, now again, this is one of these things that's a little bit hard to understand from purely static pictures. So in the description for this video, I will put another link that shows you an animation showing how characteristic peaks are produced. But it basically works like this. Every now and then, and it's not terribly likely, but it can happen, an incoming electron will actually collide with one of the electrons that orbits the atom, one of the inner shell electrons, one of the ones that are closest to the nucleus. When that happens, it's going to knock that electron out of its shell, right? It's going to be a missing electron in one of the inner shells. Now, we'll see this in the next topic on atomic structure, but one of the rules of quantum mechanics is when electrons fill shells around an atom, they need to fill the inner shells completely first before they can start to fill the outer shells. So if you have a vacancy in one of your inner shells, an outer shell electron must drop in to fill that vacancy. Now when that happens, it will have to lose energy, because electrons in outer shells always carry a greater amount of energy than the inner shell electrons do. So it will have to lose energy in order to return to the inner shell, and it will do that by emitting an X-ray photon. Now the thing about atomic energy levels is the difference in energies between inner and outer shells is fixed. Okay? And that means that when an outer shell electron moves to an inner shell, there's a limited number of ways in which that can happen, and that leads to a limited number of photons being emitted. So rather than the continuous spectrum where there's an infinite number of different possible photon frequencies, there will only be a discrete number of photon energies that can come out when the electrons from the outer shell move in to fill the inner shell. So that explains these characteristic peaks that we see. The characteristic peaks correspond to X-ray photons that are released when inner shell electrons are knocked out and outer shell electrons drop down to fill those vacancies. And because the differences in energies between inner and outer shells is fixed, whenever that happens, it leads to the same small number of X-ray photon energies every single time. Now, once we understand that, we can also explain why we don't see these characteristic peaks at lower voltages. In order to knock out these inner shell electrons, the incoming free electron, what we call the projectile electron, must be carrying enough energy in the form of kinetic energy to actually knock them out. And we know that the kinetic energy of the incoming electrons depends on the voltage. So as we increase the voltage, we increase the kinetic energy. So therefore, it's not until we reach a certain voltage that the electrons actually have enough kinetic energy to knock out these electrons. Below that, they might encounter these inner shell electrons, but they won't carry enough energy to actually knock them out. So that explains why we don't see those peaks until we reach a certain tube voltage. Beyond that, you'll see those characteristic peaks at the same position every single time, but until you get to that tube voltage, you won't see them. And now it also explains why the characteristic peaks exist in the X-ray spectra for all metals, but they're at different positions. And the reason they're at different positions is because each metal atom has its own unique electron shell arrangements and its own unique set of different energies between those shells. So therefore, let's have a think. So therefore, if you knock an electron out of the innermost shell in a tungsten atom, and an electron falls down from the second shell to occupy that inner shell, you're going to get a different energy to what you would get if you did the same thing with, say, a copper atom, because the difference in energy levels between the inner and the second shell is different for tungsten than it is for copper. So each atom has its own unique set of energy levels, and electrons moving from outer to inner shells to fill those vacancies results in a unique set of X-ray photon energies that are released. That's why they're called characteristic peaks, because the particular positions at which they appear are characteristic or unique for that particular metal. Okay, so that is about it for this video. There are two more. The next one will deal with the application of X-rays to medical imaging, and then the final one deals with a phenomenon called matter waves and the work of de Broglie, a French physicist from the early 20th century. Okay, bye-bye.